Okay, so the big news is Monday is the first exam. And this is going to cover everything, basically everything we've done so far, everything up through particle kinematics. So that can include vector stuff. It can include stuff from the math questions. And then particle kinematics, we did the relationships between position, velocity, and acceleration, the derivative relationships. We did the chain rule. We did circular motion and relative motion. So I'm just planning to put problems up here and give you time to work through them, get some practice with this stuff today. Before I do that, does anyone have any homework questions you want me to go over?
Number 18.
18. Particle kinematics. Okay, yeah. Well, I'm going to do this the easiest way. Okay, so that incline is 20 degrees, radius is 5 centimeters, angular velocity is 20. It's rolling down the incline. And we're trying to express the velocity and acceleration in a unrotated coordinate system. So this is 20 degrees. Angular velocity, 20 and 15. Okay, so it has an angular velocity this way of 20 radians per second. And it has an angular acceleration the same way of 15 radians per second squared. And the radius of this thing is 5 centimeters. So I'm going to start out with a coordinate system that's oriented with the incline. We'll figure that out, and then we'll worry about changing coordinate systems. If you think of omega as, so the z-axis, the positive z-axis is going to be coming out towards us. So omega and alpha, you can think of both of those as negative. And so the velocity vector is going to be negative omega times r which is negative of negative 20 times 0.05, 0, 0. Or that just comes out to 1, right?
Yes.
And the angular acceleration, the acceleration of the center is just negative angular acceleration times r. And so that's going to be negative of negative 15 times 0.05 so that's going to be 0.7500. And now that you have that, how do you put it in a coordinate system? So we have this stuff in this rotated coordinate system. And we want to re-express it in this coordinate system. Okay, well, if you draw these vectors in the coordinate system that we want, so okay, we want it expressed in a coordinate system like that. The velocity is just straight in the direction of the old x-axis. So this angle is 20 degrees. And the magnitude of it is 1. And so you can do this as the velocity in this coordinate system is 1 times cosine of negative 20, 1 times sine of negative 20, and so that is 0.94, negative 0.3420. And then for the acceleration, it's this way, but it has a magnitude of 0.75. This is still 20 degrees. And so the acceleration of the center is 0.75 times cosine of negative 20 degrees, 0.75 times sine of negative 20, 0. Can someone tell me what those are?
.705 and negative 0.257.
Okay. There's a really nice way to do this that we haven't talked about in this class yet, but we talked about it a little if you took statics from me, and we've talked about it in D-form a little so far. And that's using rotation matrices.
Very useful.
Yes. Okay, so say you have a vector expressed in one coordinate system, and you want it expressed in a coordinate system rotated theta, an angle theta, about the positive z axis. Then that rotation matrix, we're going to call it Q. I think that people always call it Q, and I think it comes from some kind of Latin thing. I don't remember what, but okay. And so the rotation matrix here is going to be cosine of theta, sine of theta, 0. Negative sine of theta, cosine theta, 0, 0, 0, 1. So in our case, we're starting with this coordinate system. Nope. We're starting with this rotated coordinate system. And we have the vector expressed in that coordinate system, and we want to re-express it in this. Okay? So you have to think about the right-hand rule to think about whether this is a positive or negative rotation about the positive z-axis. The positive z-axis is out of the page, so that's a positive angle of 20 degrees that we have to rotate this coordinate system. Any questions about that, the positive or negative? We're just trying to go from the one on the left to the one on the right. So theta is equal to positive 20 degrees. And so our rotation matrix is cosine of 20, sine of 20, 0. Negative sine of 20, cosine of 20, 0, 0, 0, 1. And that comes out to be 0.940, 0.342, 0, negative 0.342, 0.940, 0, 0, 0, 1. And then we're just going to multiply that matrix to the answers we got in the old coordinate system. So V in the new coordinate system is 0.940, 0.342, 0, negative 0.342, 0.940, 0, 0, 0, 1, times V in the old coordinate system, and what you get out of that is 0.940, negative 0.342, 0. And the new acceleration is this same matrix times 0.7500. This is the acceleration in the old coordinate system, and that comes out to be 0.705, negative 0.257, was it?
Yep.
0. Okay, so since these in the old coordinate system were nice simple vectors, it was pretty easy to just think of what they would be in the components of the new coordinate system on your own. Just think about what those vector directions mean and stuff like that. But you can imagine if you had vectors with all three components, and you wanted to re-express them in a new coordinate system, it can be sort of a pain. It's not so difficult, really. You just have to do it 3 times with all 3 components. But it's so much faster and easier to use these rotation matrices. And all of your calculators will just do this matrix multiplication for you. So anytime you need to switch from one coordinate system to another but keep the vector the same, there's a rotation matrix that'll just do it for you in one step. And we haven't talked about it really in lecture at all yet, but we will later on a little bit.
See, that's how I started, and then I checked my work on the D2L solution page, and it had a completely different method, and it got the wrong answer. But I ended up doing it that way, and that's why it was confusing.
Okay, that's not good.
Halfway through, it was like, wait.
Okay, sorry about that. All right. Well, you can't win them all.
Question, for the acceleration, why wouldn't you use the wall? So you don't use the whole watermelon formula, I guess I did.
Yeah.
Why wouldn't you on this one?
Because we are just calculating the acceleration of the center.
Oh.
So it does come from the watermelon equation.
Oh, that's right, because the radius is.
Yeah, but you have to use relative motion too, and the derivation is a little messy. So instead, just remember that if all you're doing is calculating the velocity and acceleration of the center of a wheel or a sphere or whatever that's rolling, then you just do it using these 2 formulas. But then if you wanted to then calculate the velocity and acceleration of points around the thing,
Yeah.
you would use this fact about the center and then use relative motion with the watermelon equation and the velocity equation for circular motion.
That makes sense. You take the point on the outside to the middle.
Yeah.
Around.
Exactly. Any other questions about this one that don't involve the solution posted on D2L? Okay. Any other homework questions you want to see?
If we could quickly look at 20.
Yeah.
I think
I don't know how quickly I can, but. Okay. So 0.72 meters is the diameter, constant speed of 8 meters per second. So let's imagine it going this way. The radius is half of 0.72, so 0.36. And the velocity of the center to start with is 8. So I'm going to use a coordinate system like this. So it's 8, 0, 0. Okay, so if it's moving 8, 0, 0, let's first figure out what acceleration it needs to stop over that. Is it a distance it gives? Over a distance of 10 meters. Okay, so we can use, the kinematics equations. I mean, I suppose really this is a chance to make sure that you're understanding the derivative relationships. So, okay, so how hard would that be to do? Well, we know that the acceleration is the time derivative of the, let's just think of everything in the x direction right now. So the acceleration is the time derivative of the x velocity. And so if we so we could think of this as, so we're going to think of this as a constant. And you can use separation of variables. You get dvx is equal to a dt. So vx is equal to at plus this. I'm sort of glossing over the whole boundary conditions thing that would get you this. We've done similar stuff to this before. And then you get dx dt is equal to at plus v0. So dx is equal to at plus v0 dt. Integrate both sides and you get that x is equal to this. And now from this equation, you can figure out that t is equal to vx minus v0 over a. And so plug that in, substitute that in here, and you get that x is equal to x sub 0 plus v0 times this thing that we just figured out for t. Plus 1/2 times a times t squared, which is vx minus v0 squared over a squared. So x is equal to x sub 0 plus v0 vx minus v0 squared over a plus, cancel this and this, and you get vx minus v0. I'll write it out fully.
You put x0.
Yeah, thank you. All over 2a Well, I'm too far to stop now that I realize this is kind of ridiculous, but plus, multiply this out, Vx squared minus 2 V0 Vx minus V0 squared. I'll make all of these 2's. So this is over 2a, and then this is all one big fraction. So that cancels that. Did something, oh, because this is, this should be plus. And so we got x is equal to x sub 0 plus. V x squared minus V0 squared all over 2a. And so we get x minus x sub 0 times 2a is equal to Vx squared minus V0 squared. Good Lord. You could just look that up in your frickin' Physics 1 notes too and skip all that. Okay, but here's our equation that doesn't involve time. Okay? Like you've never seen this before.
I'm so glad I looked up kinematic equations, just saw the links out time.
Yeah, right. Just take the one. Skip all the, that's too much. But that's how you can get it that way. Okay. So now, what are we trying to do? We're trying to figure out what's x minus x sub 0? 10 meters, yep. And we're trying to figure out that acceleration. And Vx squared is 0, V0 squared is 8 squared. So we got 20a is equal to negative 64, so 32. So a is equal to negative 3.2 meters per second squared. Okay. So now, so our acceleration vector is negative 3.200. And that's the acceleration of the center of the wheel. And so we know that has to be equal to negative alpha times the radius of the wheel, 0, 0. That's the formula for the acceleration of the center of a wheel. And so finally, we just have 3.2 is equal to negative 0.36 alpha. Nope, I already canceled all the negatives. And so, what's that, 8/9? So alpha is equal to positive 8/9 radians per second squared in the z direction, you know. So this is 0, 0, 0.8 repeating.
Got 8.89.
I think we're supposed to divide alpha, actually 3.2 over 1.36. So it should be.
Oh, 3.2, not 0.32, right. So this should be, what, 80 over 9? And so this should be 8.8. Yeah. Okay. Don't pay attention to this part. Pay attention to the other part. You know, you can just look this up in your physics book or your notes. But the idea was we had the velocity. We can use just constant acceleration kinematics equations to figure out the acceleration it takes to stop over 10 meters. And then we know from rolling without slipping the relationship between the angular acceleration and the acceleration of the center. Okay. Any other questions about that one? You're like, can we just really quickly glance at this one problem? I'm like, sure, let's derive it all from the Zermelo axioms. Okay, any other homework questions you'd like to see? Okay. Well, let's go through a problem or two. So let's say we have a longer body that's connected to the ceiling by a pin joint, so it's free to swing, and then a shorter body that's connected to that at the center. Let's say that this is 30 degrees. Here's our point P. Let's call this point A and this point B. And the length of the body that's vertical at this instant is 2 meters. And the length of this body is 1 meter. And let's say that this has an angular velocity of 5 radians per second, but no angular acceleration. And let's say that this body has an angular velocity this way of 6 radians per second, and an angular acceleration the other way of 15 radians per second squared. And we'll use this coordinate system. I don't know if you've ever seen that that way of representing the direction of an arrow into or out of the page before, but if it's like that, it's like you're looking at the point of an arrow, you know, so it's coming out towards you. And if it's going into the page, they draw like an X, like you're looking at the feathers of an arrow, you know. Okay. So let's first calculate the velocity of that point P. And remember that the velocity of that point P, you can think of that as always, if it doesn't say what it's relative to, that's the velocity relative to the ground, which in this case we could think of as, notice that pin A is fixed to the ground. So we could think of this as relative to A. So first, let's start by writing out the relative motion equation that we're going to use for this. Okay, so just take 1 minute or something and see if you can write out the relative motion equation that's going to be relevant for this velocity. So there are really 2 ways to do this, and they're both perfectly fine. The first one is, you know, if you see a way to write this out in terms of all the stuff that we can calculate in a way that satisfies that fraction multiplication equation, then do that. So you can write this out as velocity of p relative to a is equal to velocity of p relative to b plus velocity of b relative to a. And now this is circular motion of that point B around A. And this one is circular motion of the point P around B, you know? So that's great. But you also can just start writing these things down, right? You know, start out by what you're trying to calculate, say, write stuff down, and then if at the end the fraction multiplication thing isn't in the right order, then change terms until it does work using the fact that the velocity of something relative to something else is the negative of what you get if those subscripts are switched. You know, so you can, either of those will always work. Okay. Okay, so now this one is circular motion of B around, of P around B. And this one is circular motion of B around A. So let's start with the red one. So take a couple minutes, compare answers, ask me stuff if you need a hint, but we're going to calculate velocity of P relative to B. All right, so now we're dealing with the circular motion of B around A. So the relevant angular velocity here is positive 5. So omega is 0, 0, positive 5. R is from the center of the circle, that's A, to the point that we're calculating the velocity for, that's B. So this is going to be 0, negative 2, 0. And so the velocity of B relative to A is 0, 0, 5, crossed with 0, negative 2, 0. And you get 10, 0, 0. And so all together, the velocity of P relative to A is 1.5, negative 2.6, 0, plus 10, 0, 0, or 11.5, negative 2.6, 0. Any questions about that? Okay, so now for part B, we're going to calculate the acceleration. I guess we'll probably just have time to set this up, but I think really just if you can make sense out of setting these up, like the rest is just remembering how to plug it into your calculator and stuff. Really the hard part is the setup. So we're going to do the acceleration of P relative to A is equal to the acceleration of P relative to B plus the acceleration of B relative to A. This one is the circular motion of P around that point B. And this one is the circular motion of B around A. All of the R vectors that we figured out in the first step are the same R vectors as now. Just remember that for each one of these now, this is the watermelon equation. Anytime you're calculating the acceleration of a circular motion, you're going to use the watermelon equation. Okay, so I guess let me just do this, but the acceleration of P relative to B, all right watermelons will rot. We already know R. We already know omega. So, but we need to know alpha for that second body, that diagonal body. Alpha has a magnitude of 15 radians per second. It's going to be in the z direction. Is that positive or negative? Yeah.
Positive.
Right. And that's from the right-hand rule, you know, that angular acceleration has your thumb pointing in the positive z direction. So alpha is 0. Omega and R are the same as they were before. -6. And R is 0.433, 0.250. So now it's just a matter of plugging those into the equation. And the acceleration question?
Isn't the alpha 0,015?
Yes. I'm looking at the wrong one, thinking of the wrong one. Thank you. Positive 15. I just walked up there and did that. And then to calculate the acceleration of B relative to A, that's watermelon equation. This is the one that has an alpha equal to 0. This one had an omega of 0, 0, -5. And an R of 0, -2, 0.
Would it be positive?
Yep. Yes, +5. Okay, any questions? All right, that's all. So have a good weekend. I won't give you an assignment, so just get ready for the test on Monday.